Good morning, everybody. I hope you enjoyed the dinner last night, and welcome to Thursday, the fourth day of the conference. Today we have two physicists, as an exception from the other days, and we will start with Barbara Soda talking about her approach.
Thank you. Thank you. First of all, can you hear me well? All good? Okay. Yeah, so first of all, I really would like to thank the organizers, Guy and everyone else for inviting me to speak today, especially because I think you were maybe inspired to invite me because of this paper that you saw uh, published. But then because of your invitation, I was encouraged to further develop the ideas. So, just thanks to your invitation, it moved me into motion. So that's always nice when that happens. Okay, so the first part, the first part is Emergence of Spacetime from Fluctuations. That was the already published paper, and Dynamic Oblique Rotation is something new. Okay, so let's start. So what was my motivation behind all of this? So as we all know, local Lorentz symmetry is a fundamental symmetry of laws of physics, and typically we don't even question the fact that Lorentz symmetry is a fundamental symmetry. But then I find it curious that time and space, we treat them as similar enough to be mixed in Lorentz transformation, but there's tension there because we always nevertheless keep them clearly separated in the Lorentz signature. So on one hand, they are very similar enough to be mixed, and on the other hand, we always need to keep them separated. So there's nothing a priori wrong with that. Everything works. We can do physics. But it's an interesting question. Can we try to explain that on a deeper level of analysis? Especially because, in my opinion, time is a kind of a mysterious part of the world around us and physics. And I would like to understand time better. What is time? Why does time flow? Why does it flow only in one direction, and so on? Okay, so that's the motivation. But the outline will consist of two parts. First part is the published paper with Markus Reitz and Achim Kempf. It's roughly speaking a quantum gravity path integral based on spectral geometry. In this path integral, we'll see we have a gravity action and free fermions and free bosons, and we'll see that some observables are computable and even analytically. So it's very nice. We get an effective dimension of space-times that come out of the path integral, expected volume and number of degrees of freedom of the expected space-time, and we have a consistency check that works out at the end. That's part one. And then part two is the long expected adding of interactions. So this is what we were announcing in the original paper, but then Marcus went outside of physics, and you know how things are, so it takes a long time. But anyway, so I add interactions here, and now we have gravity plus interacting fermions and bosons. And what's interesting that what can happen is a change of the effective signature. So we start from Euclidean signature, and we see a change of effective signature due to field fluctuations induced disorder. And if you've studied condensed matter, maybe it's ringing a bell that we are seeing Anderson localization of some degrees of freedom. And so I call this Anderson localization of space-like dimensions into time-like dimensions, or dynamical Wick rotation. Okay, so that's just the teaser. So part one, I'm going to describe the original path integral. The motivation behind this work was, so there is some philosophy behind this, is to view correlations of things that exist in the universe as primary rather than the representation of those correlations that we see in low energy. We see a representation of that as a spacetime as a nice manifold hosting matter as quantum fields on it. So that's a nice low energy picture that we know that's well tested and that we don't contest at all. But our view is that this is this is a representation of a wider set of possibilities that could be true. And so the question is, could this picture, which we would call geometric regime, why? Because the spacetime is represented as a nice manifold. So the question is, could this picture of geometric regime emerge from some pre-geometric regime? And could it emerge multiple times at different energy scales with different dimensions? So obviously, if you want to have a mathematical framework that captures both this nice low energy picture that we know and love, and then we are also looking for something that doesn't have a nice geometric representation, the challenge is to find a mathematical framework that captures both those regimes in one. So then you can say, okay, in this limit, we see a geometry. In this limit, we don't see a nice geometry. We want to have both in one mathematical object. And so what we did is we chose the path integral formulation. What we had to do to achieve our goal is to make it somehow independent of position basis. Once you don't need to have a position basis, then you can exit the geometric regime. So remember, geometric regime means that you have a manifold, therefore you have a nice position basis probably, and so on. Okay, so that's the motivation behind it, the philosophy. What's the physics? What's the math inside it? So first of all, we have, as I mentioned in the introduction, we assume Euclidean signature. We would have preferred at that time, of course, to do Lorentzian signature because we didn't think that maybe Euclidean signature is more fundamental than Lorentzian. It's just that mathematical tools are readily available when you assume Euclidean signature. For example, you'll see this Hawking-Gilkey formula, and it's just, I think, a fact of life that a lot more work has been done mathematically on signature, on manifolds with Euclidean signature than Lorentzian signature. So anyways, we chose to formulate our theory in the Euclidean signature. Then we had to choose what we will put into our theory. So we put in gravity, free fermions, and free bosons. Now, how do you represent these pieces of the equation? Remember, I announced that we formulated this path integral in terms of spectral geometry. Okay, so what does that mean? Usually, if you're doing a path integral formulation of quantum gravity, you have to deal with diffeomorphism invariance. So somehow you have to mod out this large symmetry, and that's a problem. We avoid this problem. By using this formula. Okay, so a little bit of background. This formula, and in fact, it doesn't have to be in 4 dimensions. It can be in n dimension, and it's valid for Riemannian manifolds. This formula was done by Gilkey in 1975. It's a math paper. So it tells us that if you have, in fact, I think I drew a picture now so that we can all visually understand what's going on. So if you have a nice compact manifold, as I said, it can be in n dimensions, doesn't have to be 4. And you have some second order differential operator. You assume that there is a UV cutoff. That's another assumption that we use in our formulation. There's a hard UV cutoff. Then this formula relates a gravitational action on the right-hand side that is valid for this manifold to the number of eigenvalues of the Laplacian that acts on the manifold. Okay, so that's the visual thing, and we can go back. We can go back to this slide, And that's what I wrote here. So this is the curious formula that we end up using as the gravitational action. So instead of using all of this in our gravitational action, which would be kind of normal, the usual, we just end up using the left-hand side, which is the number of eigenvalues of the Laplacian operator. Notice that because it doesn't have any position representation, it's a nice basis-independent way of formulating a gravitational action. Okay, so we use n number of eigenvalues of the Laplacian below the UV cutoff times some constant of proportionality. We use that as the action for gravity. And note that this can be written just as the trace of the identity operator on the Hilbert space of the Laplacian operator on that manifold. So it can be written basis independently. Okay, so that's our gravitational action. Sometimes we call it Hawking-Gilkey formula. Gilkey came up with it, but Hawking used it in one of his papers, which is how we came to know it. So we use that terminology sometimes. Yeah. Well, so it's not going to be just the Einstein-Hilbert action. It has like its higher order corrections. Yeah. Yes. They are up to a constant there. Yeah. Mm-hmm. Well, you can imagine a Laplacian acting on a manifold, and then you can figure out what are its eigenmodes and eigenvalues, and then if you go only up to a certain level of eigenvalues, you cut off. That's why you have a finite number of eigenvalues. Yes, by setting a hard UV cutoff. That's set by lambda. Okay, so that's our gravity action. It's just proportional to the dimension of the Laplacian operator's Hilbert space. What about the bosons and fermions? Well, for bosons, we use Klein-Gordon fields, except we don't write them we don't write the action in the usual way. We've all seen that action. I didn't even put it there. Usually it's represented in the position basis. Then to make it independent of the position basis, we write it in this way as just the trace over this operator. Now imagine if you take the trace over the position basis, at least formally, you can get back the standard representation of the action. But because we can write it in this way basis independently, we choose, instead of representing in position basis, to represent it in the Laplacian eigenbasis. And so these what appears in the Klein-Gordon action in this basis is instead the eigenvalues of the Laplacian, the lambdas. And then instead of coefficients of the scalar field in the position basis, you get the coefficients in the Laplacian eigenbasis. Okay. And so this would be the action if we had only one species of bosons, but we said, okay, we'll put NB species of bosons. So that's why we have another sum that goes from 1 to NB. So this action just tells you have NB free bosons, and they are just nicely represented in the Laplacian eigenbasis. For the free fermions, we essentially just take the square root of the Klein-Gordon fields. You can start with the Dirac action, write it independent of the position basis, and end up again in the eigenbasis of the Laplacian. Again, the eigenvalue of the Laplacian appears, but this time instead of as lambda, it appears as square root of lambda. That's consistent with the idea that Dirac field is some kind of a square root of the Klein-Gordon field. And then these thetas are the Grassmannian components of the fermionic fields in the eigenbasis of the Laplacian. So that's it. We have all of the ingredients. We have a gravitational action, which is written in a very unusual way, but it's mathematically valid. We have free boson, free fermions, and then we put them all together. And we put them all together into a path integral. Okay, so this is where the total action is appearing. As we said, everything is a Euclidean signature, so therefore this is not an e to the is kind of path integral, but it has a temperature instead. What are we summing over? We are summing over all possible values of the components of the field in the Laplacian eigenbasis. So we are just summing over every possibility. And we are summing over every possible spectrum of the Laplacian, right? So any Laplacian spectrum that you can come up with, it appears in this path integral. Another thing that we are summing over is how many eigenvalues does the Laplacian itself have. So if you can imagine, if you have a hard UV cutoff, if it's a very small manifold, it can have maybe only one eigenvalue. And then if it's a much larger manifold, there will be more eigenvalues up to that cutoff. So this is roughly speaking something like a sum over sizes of the manifold. Yes? Yeah. So the spectrum is always finite and discrete, unless you look at maybe there are some clustering of points in some extreme cases. So we didn't. What we did in this work is, instead of maybe some approaches think ahead of time what kind of weight I should put on which spectra so that I get certain geometries out of that, we took a different path in this work where we just assumed uniform distribution, and then we have a consistency check at the end, right? And I will tell you about it. So we didn't get into this trying to adjust the spectrum towards a certain outcome. We just said uniform distribution of the spectra, and then we do a consistency check at the end. That's my answer. So any possible spectrum. So this is 1 over n factorial. That's just preventing overcounting. So no spectrum appears twice in the path integral. Every possible spectrum, discrete finite spectrum, appears once. Does that make sense? Oh, it's an assumption. Yeah. Okay. Yeah, I think that's what we were just discussing. And as I said, we are summing over all possible field values given in the Laplacian eigenbasis and all possible Hilbert space dimensions given as integers. Okay. So what because we assumed free fields, it would not surprise you probably that we can evaluate this path integral analytically, even though it's a quantum gravity path integral. Luckily, the way gravitational action comes in is simple enough. It comes in as just this factor of n, so number of Laplacian. So it ends up being something like like a bit more complicated sum of Gaussian integrals. It's not that bad, and because it's not that bad, we were able to evaluate the path integral analytically. Yeah, just one comment: the fermions and bosons are free as written in the action, but they are weakly interacting through gravity, right? The n factor in the action is it is making them interact even though weakly. Okay, so we evaluate the path integral, looks relatively decent. And so what can we get? So we have evaluated the path integral. What can we get out of it? What kind of observables? One interesting observable we could calculate was the effective dimension of emergent spacetimes. So how did we do that? We looked at the probability distribution of eigenvalues that come out of the path integral. And then we use the Weil scaling law. So there are different ways to, in quantum gravity approaches, to find dimension of some object. We found that Weil scaling law was the most appropriate one. If you don't know what it is, Weil scaling law roughly tells you, even if you remember quantum mechanics from undergrad. So if you have some box and you have a confining box in which you are now calculating the eigenvalues in that box at high energies, it doesn't matter what the shape of the box is anymore. The only thing that matters for the behavior of the eigenvalues is the dimension of the box. So you'll get a different scaling if you are in a two-dimensional box, if it's a particle in a two-dimensional box or a three-dimensional box. So the kinetic energy in the Schrodinger equation is also just a Laplacian up to a constant. And so we can use the Weil scaling law here because we can calculate the behavior of the eigenvalues. Okay, and the Weil scaling law tells us that the dimension, so to speak, of the box, in this case it's a compact manifold, the dimension of the compact manifold is related to the scaling of the eigenvalue probability distribution. And so what we find in the simplest case of a trivial mass spectrum, that means all of our free bosons and fermions have the same mass. What we get from the simplest case of trivial spectrum is that the effective dimension of space-time is determined by the difference in number of fermion and boson species. So it's a difference of their numbers plus 2. That's an interesting result. Especially people have commented. I think that when you have supersymmetry, you end up getting 2, which is kind of curious, and it appears in other places. Okay, so that happens when you have the trivial spectrum. What about when you have a different mass spectrum, so different particles have different masses? Well, then you need to refine the formula, and you have to basically look at plateaus of the probability distribution and use just a slightly more complicated formula. And then what you see is that you can get at different energy scales different effective dimensions for space-time. That happens because imagine if you have a non-trivial mass spectrum, you have different masses for different particles. At higher energies, you can unlock new species of particles, and that changes the effective number of fermions and bosons, so it can change the effective dimension in that regime. So this is an example that I usually show, where we chose the exact, the mass spectrum and the number of fermions and bosons, so that you can have at low energies a 4-dimensional spacetime, then some kind of a phase transition where the spacetime is no longer necessarily in a geometric phase, maybe it's doing something weird while it's transitioning to a new plateau of a 2-dimensional spacetime at higher energies. So this is not a necessary result from our theory. Our theory is not predicting, it's not telling you, okay, this is how many fermions and bosons you're going to have, therefore these are the dimensions of spacetime. But what our theory is telling you, if you put in this many fermions and this many bosons, and they have a non-trivial mass spectrum. What you can see is a change of dimension of spacetime, and then the details of how many dimensions at which energies, that depends on the the mass spectrum and so on. Okay, so that's the most, I would say that's the most interesting result of that. Oh, one more thing that is interesting about that is that this has a similar, spacetimes in this path integral have a similar behavior to neutron stars. So if you add more bosons, it makes the dimension of spacetime smaller. And if you add more fermions, it pushes it out. It makes the dimension of spacetime higher. Okay, and so now we're going to get into what I mentioned earlier, which is this consistency check. Okay, so for the consistency check, we calculate two more observables. The first one is the expected number of degrees of freedom of the emergent spacetimes, and that's relatively easy to calculate, kind of same way that you would do it in thermodynamics. Again, we get a nice analytical expression. Okay, so that's the first statement, is that we can find relatively easily the expected number of degrees of freedom. The second observable we can get to relatively straightforwardly is the effective volume. So how do we find the effective volume? Well, we know that spectral gap of the Laplacian, so that's the difference between the first and the second eigenvalue. We know that the spectral gap of the Laplacian scales as 1 over L squared. And roughly the volume scales as some length scale to the d power, if d is the dimension of spacetime. And so we can find, long story short, we can find the effective volume of spacetime from the gap. So earlier we found the expected distribution of eigenvalues of the Laplacian. Now we are going to find the expected gap. So that's a difference between the first eigenvalue and the second eigenvalue. And from that, we get the effective volume. Okay. And not to get into maybe a bit complicated formulas, I think the pictures is much more clear. We see that the dashed line is the expected number of degrees of freedom. So that's n, expected value of n. And the solid lines are the expected volume, and they are basically following each other. We can also discuss maybe different behaviors of these observables, but why do I focus on the fact that they are roughly always following each other? Well, that's the consistency check. So recall the formula from the beginning, where Hawking and Gilkey show us that n is related to some gravitational action. Don't forget that there are higher order corrections, that's important. But it approximates the Einstein-Hilbert action in some regime. Okay, so this formula tells us that classically, for the classical formula, it's just valid for a classical Riemannian manifold, the density of degrees of freedom is constant up to some higher order corrections. And now the question is, after we quantize this formula in the way that I just described with the path integral, how does this get corrected, the classical formula? And it's nice that we get the result that density of degrees of freedom is still constant up to some corrections. So this is why in some sense it's justified, even though we made some leaps of faith in the beginning when we formulated the path integral, why it comes back self-consistent is exactly because this formula tells you that the number of degrees of freedom, it just gets corrected after quantization. So maybe something that I should comment while we are at this workshop, oops, that's wrong, is that when we are summing in the path integral, when we are summing over all spectra, some spectra correspond to nice manifolds, but not all spectra correspond to manifolds. So this path integral in that sense is a little bit wild. So because you're summing over nice geometric stuff, and also you're summing over stuff that is not geometric. And a priori, you would not expect necessarily that the consistency check comes out right? Because maybe with this kind of, you add into the path integral some things that are non-geometric. Why should the Gilkey formula still be essentially valid, right? The fact that the consistency check works out at the end is important in this path integral. Okay, so that's the first part. What we did with this work is obtain dimensions and volumes of emergent spacetimes. We saw that they depend on gravity, of course, but also interestingly on boson pull and fermion pressure in the way that I described. It's kind of similar. Dimension behavior is kind of similar to neutron star behavior. We saw that this balance of gravity, boson pull, and fermion pressure depends on energy scale through the mass spectrum. And this theory can yield energy-dependent spacetime dimensions and emergence. So you can think of this as different nice geometric representations of spacetime emerging at different energy scales. And we showed that an important consistency check was okay. So as a summary, we find that the low energy picture of spacetime as a manifold hosting matter as quantum fields can emerge from a pre-geometric regime at different energy scales and with spacetime changing dimensions. And so this was the published work, and we were very happy with that. We were maybe a bit curious about the fact that it's in Euclidean signature. Maybe you want to change it to Lorentzian signature. Maybe you also want to add interactions between fields, because this, if you want to see a more predictive theory of nature, you want to be closer to the description of nature, and we know through the standard model that we need to have interacting fields. Okay, so this will be this second part, is what happens when we add some kind of a field interaction to the path integral, and what happens to the signature. Okay, so as I said, I was looking at how to add interaction to this path integral. And in fact, I ended up being motivated by invitation to this workshop, and also just by thinking about certain aspects of time. And so after lots of thought and attempts, I just added the simplest thing I can think of, which is the Yukawa coupling. So now the total action consists of gravity, and with the action that we saw before, free fields, some Yukawa interaction. Once again, we write the interactions in the eigenbases of the Laplacian. The philosophy still remains the same. We want to get rid of the assumption of position bases. And so it looks like this. These are just components of the fields in the Laplacian eigenbases, and these are some coefficients that are created by an overlap of the eigenstates of the Laplacian. And we proceed to integrate out the field's degrees of freedom for the full path integral. Okay, so there are more degrees of freedom than just the fields. Remember, the original path integral had fields degrees of freedom, but also the Laplacian eigenvalues and some sum over n. But because I was thinking about time and I had some intuition, I just integrated out the fields degrees of freedom, and I wanted to look at what happens to the geometry. Okay, and so what we find, I mean, this is nothing new. This is just, it makes sense when you integrate out the fields. we know that quantum fields have their fluctuations. We can view this as some kind of a source of disorder for background geometry. And if you want to do this, calculation, for a finite Yukawa coupling, that's hard, maybe impossible. I don't know what people can do. So what I instead did, I went into two regimes, which is assumption of weak coupling and the assumption of very strong coupling. Right? Typically, when you make things extreme, it decomplexifies the calculations. And what I found was in the weak coupling doesn't change the sign of the probability distribution for the eigenvalues of the Laplacian. So everything is fine. You still have maybe slightly slightly modulated probability distribution for the Laplacian eigenvalues, but it's still the assumptions of Euclidean signature are still valid. Right? Maybe you'll get slightly different spacetime in the expectation value, but everything is pretty much the same. But if you assume strong coupling for the Yukawa interaction, that changes the probability distribution it changes the sign of the probability distribution for the eigenvalues. And the statement, as long as the coupling is greater than a critical coupling, I don't have a proof of that statement because the calculation was only done for a strong coupling, but I will tell you in a moment why I wrote that. Yes. No. So the idea is that the probability distribution itself now becomes instead of going just from 0 to infinity, which or whatever from 0 to some level, it's that's consistent with all the assumptions that you started with, which is Euclidean signature. But now, when you get into this regime of strong coupling, you start getting as much of a positive probability distribution as negative. So you can redefine the negative ones as positive, but only now the eigenvalues are going from negative to positive. So that's a sign that you have now entered the regime where the signature is Lorentzian, or it doesn't have to be in general Lorentzian. That will be a discussion a little bit later. It can be maybe multiple dimensions have changed signature. Yeah. Yes. It can be negative. Yeah. Okay. And so why do I find this interesting? What was anyways the motivation to do these calculations in the quantum? Yeah. What do you mean by that? Yeah. I mean, there's definitely some tension, and more work needs to be done. I don't know if I can give you the exact answer to that, but I can just tell you a little bit more about why this makes sense, this calculation, and then just keep accumulating either evidence for or against this kind of idea. Yeah, so yeah, that's a good question. How does it, maybe there should be a calculation going back of how does this affect the initial assumption of the gravity, but I'm not sure exactly how that would look. Okay. Okay, so this might look really strange, bizarre calculation. Now all of a sudden we are getting signature change from interactions. We have not seen this before, at least I have not. But what's interesting is that this idea came from condensed matter, and it comes from something that was discovered a long time ago by Anderson. It's called Anderson localization. So what is Anderson localization? In everyday terms, in perimeters bistro, we have this kind of weird, maybe artistic sculpture above the tables. And the way you can see this pragmatically, not artistically, is that this allows for a random potential in the space. And random potential, when you have it, you can sometimes get into a regime where instead of the eigenmodes of whatever operator you have there, let's say you have a Laplacian plus some corrections for the sound for sound of human speech, they, instead of propagating, instead of being oscillatory, they start being localized. So the whole idea of putting that in parameters bistro is to absorb sound so that it doesn't echo, come back and forth. And that's the principle of Anderson localization. It also appears when you go to music halls. Sometimes they put random potentials essentially in the back of the music hall. Okay, so Anderson in 1958 discovered that disorder can localize wave functions. One easy way to think of it is that if you have a Schrödinger equation, kinetic energy plus some random potential, typically you would expect if this random potential is very small, let's say in one dimension, if it's a very small potential, it's not going to do much. You're still going to have nice oscillatory wave functions, and everything works out as usual, except that's not true at all. In one dimension, for free particles, any tiny random potential, or you can think of it as disordered because it doesn't have to be random, it can be just kind of quasi-random. So any kind of tiny random potential will fundamentally change the behavior of eigenfunctions. They'll start being localized, right? Like instead of being nice oscillatory wave functions, they become localized. So that's what Anderson discovered in 1958. And in recent times, there has been progress on analytically understanding Anderson localization. That's very important because for most of the development of this phenomenon, you had to use numerical methods, which is for many people unpleasant and just not clear enough to do. And so maybe one comment that's important also for the quantum gravity path integral is in one spatial dimension and two spatial dimensions, any small disorder will do. Any small disorder will change this behavior of eigenfunctions from oscillatory to localized. But in higher dimensions, you need a critical amount of disorder. So there's a notion of in high dimensions, and also when you have weakly interacting particles and so on, that you cannot just change the behavior of all your modes just by having presence of disorder. There needs to be a critical amount of disorder. So one way to think of that is instead of having little bumps in your potential, you need to have bigger bumps. That's a good way of thinking about it. Okay, yeah. Do I have an intuition? Yeah, I don't know right now. Yes, I think that, yes, thank you. I think it's definitely related to that. I remember reading about it. Yeah. I don't have a good, unfortunately, I was not trained as condensed matter theorist, so I'm just trying to understand this better. Yeah, so the idea is that the presence of disorder changes the behavior of eigenfunctions. Okay, so what you would typically expect to be oscillatory now becomes some kind of a generally exponentially decaying function on both sides of some center of mass distribution. So it's interesting that oscillatory wave functions are solutions of this kind of differential equation, while exponentially decaying and also exponentially exploding, but that's fine. Anyways, exponential wave functions are the solution of this kind of equation. The only difference being the sign flip between them. And so a toy model in which we can think of this is, imagine you have some three-dimensional system. It's a nice Cartesian system. It has nice Cartesian boundary values, so you don't have to think too much about it. You can maybe separate variables. And so we only add a random potential to one dimensions. The other two we leave alone. Then in the x dimension, where we added the random potential, the wave functions will become localized. The idea schematically is that the starting point was a usual kinetic energy, but then after adding a disordered potential to it, we find that effective signature flip can occur. Now, this is a schematic formula. You shouldn't take it as equality. But the point is that the disordered potential changes the behavior of eigenfunctions so that they, instead of being the solutions to the first differential equation, they become solutions to the same differential equation with a flipped sign. So that was the motivation behind all of the work that I mentioned before. Basically, the idea was that disorder can source an effective signature change. In the case that I was presenting earlier, from Euclidean to Lorentzian. And this was also an attempt at answering the question from the beginning: how come time and space can be similar enough to be mixed, but then dissimilar enough to be clearly separated in Lorentz signature? If this model is true, the answer would be that time and space are made up, so to speak, of same material. If it turns out that the story is at least somewhat true, that if we have a fundamental Euclidean signature, but quantum field fluctuations are sourcing disorder that flip the sign of one of the dimensions and at the same time localize time, that means that the difference between time and space is just that time is a small dimension, is a very localized dimension, while spatial dimensions can be related to this oscillatory representation, which is extended, right? That's a major difference between oscillatory wave functions and localized wave functions, that one is small, so to speak, and the other one, it has a large extension, it's large. So that would be my answer to the original question. And maybe to comment on the quantum gravity path integral, I started by adding a Yukawa interaction, which is isotropic in all of the spatial dimensions of the Euclidean signature. The question is, how can it single out one or more dimensions for localization? Well, you can think of it in this way. When you have weak disorder, everything is still isotropic. Maybe you make some more wiggles on your manifold, but nothing radical happens. You still have only spatial dimensions. When you increase the amount of disorder, that corresponds to increasing the coupling constant of the Yukawa interaction. Some kind of a localization happens, and it happens anisotropically. So that would mean that the time-like direction would be selected as a spontaneously broken symmetry. Okay, and it's possible that if we increase disorder further, possibly more dimensions become localized, so we would have more time-like dimensions, but that's a speculation. This is something that is work in progress, and there is not much in literature even about how to anisotropically create localization when you add isotropic disorder into a system. And finally, I wanted to comment, I think I will end a little bit early. Finally, I would like to comment that there have been some discussions in the past years about Hartle-Hawking no-boundary proposal. So there were people who, Turok and others, who have claimed that the no-boundary proposal doesn't work when you assume fundamentally Lorentzian signature, and that's all interesting and it's all fine. I wonder if this kind of a dynamical Wick rotation scenario, where as you increase fluctuations of quantum fields that are then sourcing disorder and flipping the signature for one of the dimensions, if this could solve this problem, because then we would have fundamentally Euclidean signature at in this part of the no boundary proposal, and that's fine. The issue is, how does it connect to the Lorentzian signature? What we believed before is that it's always kind of Lorentzian, that the Wick rotation that happens in between is just put in by hand, but perhaps the universe does start out Euclidean, and then a dynamical Wick rotation induced by quantum field fluctuation happens, and then we get a time-like dimension. That's all. Thank you for your attention.